Welcome to Combustion Module 7, the last module in this series of topics we have been covering. We'll begin with how to balance a reaction. We'll begin this module with balancing a reaction, different kind of combustion reactions, air-fuel ratio, and we'll then produce an overview of mass and energy balance equations. Module 5, where we covered mixture of gases, is something that you go to review before covering this particular module. So let's begin with a chemical reaction. Let's say someone writes a reaction such as hydrogen and oxygen react to produce H2O. Well, this arrow is very special. It means on the left hand side, whatever we see is known as reactants. And on the right hand side, whatever you see are called products. Well, obviously you will notice that the reaction is not balanced. A balanced reaction means you have to make sure atoms are conserved. When a chemical reaction takes place, basically hydrogen and oxygen molecules, they bombard each other, they hit each other, and all these molecular bonds get broken if the kinetic energy of the collision is high enough. And then the atoms will rearrange. So we are not talking about splitting atom here. Always remember, a chemical reaction is reorganization of atoms after the molecules split apart into atoms. So when hydrogen and oxygen collide, they will make different kind of combination of hydrogen and oxygen. Let's say for some reason only H2O is in the products. Then obviously the number of atoms on the left-hand side and right-hand side of a given species must be conserved. And you must have seen a balanced reaction will be written like this. If somebody writes like this, then there are 4 atoms of hydrogen on the left-hand side, 4 on the right-hand side, 2 atoms of oxygen on the left-hand side, and 2 atoms of oxygen atoms on the right-hand side. Well, this is all you know from chemistry. Let's take a look at the same reaction from the point of view of engineering, especially combustion. So when you look at the same reaction, we'll say, the reactants are hydrogen and oxygen, products are H2O. Then a chemist will look at this reaction and say there are 2 hydrogen molecules reacting with 1 oxygen molecule. But as engineers, we know we cannot really get a single molecules. Instead, we'll use a big dozen, our kilomole as our unit. We'll say, 2 kilomoles of hydrogen reacts with 1 kilomole of oxygen, producing 2 kilomoles of H2O. We scale it up. Instead of single molecules, we look at kilomoles of molecules. Recall that kilomole is a count. How many molecules are in there, measured in a big dozen. Okay, now that we understand that meaning, second thing we do as a combustion engineer is that we identify the fuel, hydrogen in this case, and we always express a reaction in terms of a single kilomole of fuel. In that case, we can divide the whole reaction by 2 and write it like this. In other words, we have now 1 kilomole of H2O is reacting with half a kilomole of oxygen, producing 1 kilomole of H2O. Notice that on the left hand side there is total kilomoles is 1.5, on the right hand side is 1 kilomole. So the first thing, the number of kilomoles are not preserved in a reaction. Obviously, it's kind of obvious because molecules can combine to make a bigger molecule, or it can split apart. A big molecule can split apart, producing more kilomoles, more count of molecules. Okay, so now we understand that a basic structure of a reaction. Let's quickly see how we balance a reaction. Okay, for that, suppose we want to balance a reaction between, say, methane, natural gas that you see burning in your gas stove, and oxygen, producing H2O and CO2. Suppose this is given to us, that methane and oxygen are reacting, producing H2O and CO2. Well, how do you balance a reaction like this? You always assume the fuel to be 1, and we don't know the stoichiometric coefficient, so we just we'll write. So A, B, C are called stoichiometric coefficients. So our goal is to find A, B, C. How do you do that? Atoms are preserved. So we'll write hydrogen. On the left hand side we have 4, and on the right hand side we have 2B. So that solving that, we immediately get B to be 2. Okay, let's balance carbon. On the left hand side we have 1, on the right hand side we have C. So obviously C equals 1. And let's balance oxygen. On the left hand side we have 2A, on the right hand side we have B plus 2C. So B and C we already found. B is 2 and C is 1. So that gives us A to be 2. So therefore the reaction can be written as methane plus 2 oxygen going to B equals 2 H2O and C equals CO2. So make sure you can balance the reaction. It's quite simple. Of course, you have to know ahead of time what are in the products. If you know the products molecules and the reactant molecules, and then you can just construct algebraic equation for the number of atoms of each atom that appears, of each element that appears in the reaction. In this case, carbon, hydrogen, and oxygen atoms, oxygen elements are present. So it's quite simple to balance a reaction. Let's see what this reaction, let's explore the reaction a little bit further. So let's write down the balanced reaction again. Methane plus 2 oxygen going to 2H2O and CO2. Once again, to remind you, the fuel is methane here, and these are our reactants, these are our products. So the oxygen to methane ratio, one can quickly calculate. Somebody says, okay, this reaction means what? 1 kilomole of methane requires 2 kilomole of O2, producing 2 kilomole of H2O and 1 kilomole of CO2. Notice, if you know the molar mass, we can very easily convert that to mass. Molar mass of methane is what? Carbon is 12 plus 4, 16. So we can say 16 kg of methane reacts with oxygen is 32, so it's 64 kg of oxygen, producing water is 18, 36 kg of water, and CO2 is 44 kg of CO2. So notice we can very quickly convert mole into mass if we know the molar mass of individual species. Well, let's try to classify the reactions, and we'll soon try to explore a reaction like this with little more, a few more definitions. For example, a reaction of this type where reactants goes to products is known as overall reaction. What does overall reaction means? That means it's kind of like an input-output or inlet-exit relationship. If we have a combustion chamber and you put some methane in, put some oxygen in, they're flowing through different tubes, let's say, they're burning, and whatever is coming out are called products. And when you connect the tube through atom balance, like in this particular reaction, it is called an overall reaction. Well, in an overall reaction, if all the H goes to H2O, if all hydrogen got converted to H2O, and if all carbon goes to CO2, these are called fully oxidized. When hydrogen is fully oxidized, it produces H2O, and carbon produces CO2. Of course, in this particular reaction, there could be some carbon monoxide or OH and some other compound, say hydrogen peroxide. In that case, this reaction is not called fully oxidized. A fully oxidized reaction is also known as complete reaction. So for example, if I go to an animation to show this to you right now, if we go to combustion, and let's see if you can find a reaction. Okay, let's go to, okay, so this is where it illustrates an overall reaction. Overall reaction means hydrogen and oxygen. In this case, 1 kilomole of hydrogen and half kilomole of oxygen are the reactants, and it produces all these different kind of species in the products. But once somehow everything is measured or somehow theoretically predicted, atom must be balanced. And once atoms is balanced, this is called overall reaction. That doesn't mean every time hydrogen and oxygen reacts, this is what is produced. In this particular reaction, this is what has been produced under certain conditions. And whenever we relate the reactants with products with a single arrow, it is called overall reaction. On the other hand, a theoretical reaction is where an overall reaction is such that it is hydrogen and carbon are fully oxidized. In other words, there is another term for it. It's called the reaction is complete. So whenever a reaction is complete, that is hydrogen and carbon are fully oxidized, and second condition is that there is no leftover fuel or oxygen at the end of the reaction, such a reaction is called theoretical reaction. So two conditions must be met. One is the reaction must be complete, and second is that no extra fuel or oxygen. And these two conditions makes the reaction a theoretical reaction. So it's a very specific term to combustion. Okay, if you, on the other hand, so theoretical reaction is basically it produces a baseline. If you complete a if you know your reactants, generally the reactants are always known. You know exactly what is going to a combustion chamber, and you construct a theoretical reaction by just assuming the carbon is going to CO2, hydrogen going to H2O. So that's quite simple to construct, and it becomes a baseline reaction. Whereas the overall reaction that we showed in this case is definitely not a theoretical reaction. On the other hand, what is an elementary steps? An elementary steps means actually what goes in a reaction. In reality, hydrogen and oxygen may hit each other and produce OH, or it may produce OH and O. And you can see many different kind of possibilities exist. Only here we are showing only 5 of the reactions. And look at the special kind of arrow, reversible arrow that is shown. So these are called elementary steps, and many of these combine together to produce the ultimate products in a reaction. To know ahead of time exactly these elementary steps is a very difficult proposition. There is a lot of research that goes on, and that area of research is called chemical kinetics, and this is covered in chapter 14 of your book. We'll not go there, but at least you should have an idea. We may use a software to predict some of these products in an actual reaction, and that's called an equilibrium reaction in thermodynamics, where you can predict this complex series of products by assuming the reaction is reaching equilibrium. Again, this is in chapter 14, and we'll use a software, an interactive actually, to show how we can calculate this complex series of products that a reaction may produce. Okay, now that we know different kind of reactions, let us construct a theoretical reaction between methane burning with air. pure oxygen, which in this particular case we built a theoretical reaction, methane reacting with pure oxygen, but pure oxygen is hard to find. If you burn something, chances are engineers will be using air from outside. Now, how do you define air? We know in air, the mole fraction of oxygen is 21% or 0.21, and of course, nitrogen will be the rest. So air is composed of oxygen and nitrogen. So you can say 1 kilomole of air means what? 0.21 kilomole of oxygen plus 0.79 kilomole of nitrogen. So that's nothing but 1 kilomole of, whenever you see 1 kilomole of air, we can write like this. But many a times, we need oxygen. So therefore, instead of 1 kilomole of air, if you want really 1 kilomole of oxygen, then you have to multiply. Notice if I want to make it in terms of 1 kilomole of oxygen, then you have to 1 divided by 0.21, which is 4.76. So if you multiply both sides by 4.76, we'll get 4.76 kilomole of air. You can see that then you'll get O2 plus 3.76 of nitrogen. See if that makes sense to you. 1 kilomole of air has this plus this. 4.76 multiplying both sides by that, we get 1 kilomole of oxygen. So in other words, if somebody says, give me 1 kilomole of oxygen, you can go around and get some 4.76 kilomole of air. In that, you're sure there'll be 1 kilomole of oxygen. So when you're writing a reaction, say, between methane and air, an easier way to write the reaction will be methane plus this much amount of oxygen and nitrogen. Of course, try to remember that molar mass of air is 29 kg per kilomole. It's a good number to memorize. And of course, molar mass of methane, we already saw. Carbon is 12, hydrogen is 1, so it's 16 kg per kilomole. So let's now balance a reaction, a theoretical reaction, a constructed theoretical reaction between methane and air. How do you do that? You write the methane plus an unknown amount of air. And this will be our formula for air. And how many kilomoles of air is in here? 4.76 is here times A. Okay, going to say B CO2 plus CH2O plus D nitrogen. Does that make sense? Because there'll be some nitrogen left over, which nitrogen is just an observer. It doesn't participate. We cannot help it because we cannot find pure oxygen so easily. So now, if you balance this reaction, I leave it to you, balance carbon, hydrogen, oxygen, and nitrogen to show the following result. Well, the atom balance will give you A to B 2, B to B 1, C to B 2, and D 7.5. 6. In other words, if I write the complete reaction, theoretical reaction, A is 2, O2 plus 3.766 nitrogen, going to 1 CO2, 2 H2O, and 7.56 nitrogen. So the question is, 1 kilomole of methane reacts with how many kilomole of air? Well, it's not 2 kilomole. Notice how many kilomoles of air? There is 4.76 here times 2. 4.76 times 2 makes 9.52. I think I made a mistake with nitrogen. 3.76 times 2 on the left hand side, so it should be 7.52. Okay, so similarly you can find so many kilomoles of CO2, 1 kilomole, etc. produced. Suppose we want the amount of air on mass basis. So on mass basis, what we get? 1 kilomole is 16 kg, and 9.52 times 29, which is 9.52 times 29 is 276 kg. So therefore 1 kg of fuel needs how many kg of air? It would be 276 divided by 16, so approximately 17.25 kg. And that is known as the air-fuel ratio. So the theoretical air-fuel ratio is 17.25 for methane reaction. So if this is our baseline reaction for methane, 1 kg of methane will require 17.25 kg for complete combustion. The combustion is complete. Why? Because carbon goes to carbon dioxide and hydrogen goes to H2O only. There is no CO or there is no OH, etc. Why the reaction is theoretical? Because there is no leftover fuel like methane or leftover